This show is about the law of definite composition and empirical and molecular formulas, and is very much a review of material from first-year chemistry. First, a tribute to Antoine Lavoisier. He explained combustion as a reaction with oxygen gas. This, of course, put a nail in the coffin of the phlogiston theory. You can read up about that on the internet. Lavoisier always made extremely careful mass measurements using the best instruments available to him. He demonstrated in many reactions that mass was neither gained nor lost. We call him the father of chemistry. Tragically, he was killed in the French Revolution. Of course, we also honor Avogadro as one of the fathers of chemistry because of Avogadro's hypothesis that formed the basis of our atomic mass scale. Let's go to Proust's law. This scientist analyzed many compounds, took them apart into their constituent elements. He determined their chemical composition by mass. He showed us that hydrogen is 11.19% of the mass of water, and oxygen is 88.81% of the mass of water. And it's always that way, no matter where you take the sample of water. And he postulated from all his work that a given compound always has the same proportion of elements by mass. We now call this the law of definite composition. How does it work? Well, it's a regularity. It suggests that each unit of the compound, say sodium chloride, is made of identical parts of sodium and chlorine. This is an intensive property. That means that the size of the sample has no bearing on the composition of the compound. It supports, of course, the theory that all matter is made of those little parts called atoms, and, as Dalton said, that the atoms are all alike. If we then know the mass of each atom, we can figure out the proportion of atoms in the compound. And that's where the atomic mass scale comes in. That leads us to the question of an empirical formula. The empirical formula of a compound is a formula that gives the simplest whole number ratio of the atoms of each element in a compound. It's of course found by determining the simplest whole number ratio of the moles of atom of each element in the compound. And it is a simple formula. So the molecular formula of hydrogen peroxide is H2O2, but the empirical formula is HO. The empirical formula knows nothing about how the molecule is made up, just the ratio of moles of atoms. Glucose and fructose have the molecular formula C6H12O6 and the empirical formula of CH2O. That's why they're called carbohydrates. CH3O has the empirical formula of CH3O. You can't simplify that anymore. And CH3OOCH is C2H4O2, and that's CH2O. But it's not a carbohydrate, even though its simplest formula looks like that of glucose. So the empirical formula gives us information on a molecule, but not all the information on the molecule. Let's look at a problem. Let's determine the empirical formula for a compound that has 2.128 grams of chlorine and 1.203 grams of calcium. Here are our steps. We find out how many moles of atoms there are, and we divide each number of moles by the smallest number of moles. So you'll need your periodic table of atomic masses. First, we find the mole amounts. 2.128 grams of chlorine is multiplied by 1 mole of chlorine per 35.45 grams, and that gives us 0.0600 moles of chlorine. The same calculation for calcium, dividing by 40.08 grams, the molar mass of calcium atoms, gives us 0.0300 moles of calcium. We now divide each mole by the smallest number of moles, and we get, obviously, for the chlorine, 0.06 divided by 0.03, or 2, and for the calcium, 0.03 divided by 0.03, or 1. The ratio is 1 calcium to 2 chlorines. The empirical formula for this compound is CaCl2. Let's do another. Compound weighing 298.12 grams consists of 72.2% magnesium and 27.8% nitrogen by mass. What's the empirical formula? Here's a little doggerel rhyme here that may be useful to you if you'd like to memorize it. So let's look at this. Now, do we have to multiply the total mass by the percents? We really don't. We could have just used 72.2 grams of magnesium per 27.8 grams of nitrogen. But let's follow along with this method. We find 72.2% times 298.12 is 215.24 grams of magnesium, and a similar calculation gives us 82.88 grams of nitrogen. We then convert that to moles by dividing the magnesium by the 24.3 grams atomic mass, giving us 8.86 moles, and the nitrogen by 14.01 grams per mole of atoms, or 5.92 moles. We then divide by the smallest number of moles to get mole ratios, and for magnesium, dividing by 5.92 gives us 1.5. For the nitrogen, of course, it gives us 1. Now that's not small whole numbers, because the last step we're going to do is multiply until we have all whole numbers, just as we know we should. So we multiply everything by 2, and we get a ratio of 3 moles of magnesium atoms to 2 moles of nitrogen atoms. That's the way you get the empirical formula. Here is some practice. Molecular formula for the colorless high oxide of nitrogen, N2O4. What's the empirical formula? And the same thing for ribose. That should be fairly easy for you to do. Now let's go to a compound of iron and oxygen, and we find 11.66 grams of iron for 5.01 grams of oxygen. We can calculate the percent composition by dividing the parts by the whole, and we can find the empirical formula quite easily by finding the number of moles of each. The compound is 55.3% potassium, 14.6% phosphorus, and 30.1% oxygen. What's its empirical formula? Do it exactly the same way. You can treat it as 55.3 grams of potassium, 14.6 of phosphorus, and 30.1 of oxygen. Go to moles, then the ratio of moles, and multiply until you get whole numbers. Now, how are we doing this empirical formula in the lab? It's very simple. We're going to heat in an oxygen stream, in this case a hydrocarbon, maybe wax or something like that, and it's of course going to burn completely in the oxygen to form carbon dioxide and water vapor. We then pass it through a water absorber that we've got the mass of, and we know that all the water that's trapped must come from the hydrogen in the compound. We then know that in the carbon dioxide absorber, which may be a compound of lithium, all the carbon dioxide absorbed comes from the carbon in the compound, and we can find the change in mass to get the amount of carbon dioxide produced. So the mass increase of the water absorber and of the carbon dioxide absorber gives us the amount of water and carbon dioxide that came out. Here's an example. Isopropyl alcohol is burned and produces 0.561 grams of carbon dioxide and 0.306 of water. What's the empirical formula? We go from moles, we find grams of hydrogen in the water. The difference is the oxygen atoms. This permits calculating the moles of all three elements and gives us the empirical formula. So even though we might not be able to immediately find out how much oxygen, if we have the carbon and the hydrogen, we know that the difference would have to be the oxygen. So let's look at that. The mass of the carbon, we might multiply 0.561 grams that we got by the ratio 12.01 grams of carbon to the 44.01 total mass of carbon dioxide mole, and that gives us the mass of the carbon. Similarly, we do the same thing for the 2/18 for the hydrogen in water. We get 0.034 grams, and once we've added these two up, we subtract it from the 0.255 grams in the original sample of isopropyl alcohol, and we get the amount of oxygen that's left. We then calculate the moles of carbon, hydrogen, and oxygen, as you see here. We divide by the smallest number, and we come up with essentially 3, 8, and 1. The empirical formula then is C3H8O. The molecular formula gives us the actual number of atoms of each element in a molecular compound. The steps are simple. We find the empirical formula, calculate the mass of that empirical formula. We divide the total molar mass by the empirical formula mass, and we multiply the empirical formula by the factor that results. So to find the molecular formula for a compound whose molar mass is about 124, and empirical formula is CH2O3, we find the empirical formula mass of this empirical formula is 62.03. We divide the 124.06 by that number and we get 2. That means there's 2 of these in a molecule of this. Therefore, C2H4O6. Here's another question that you can do now. Contains 4.90 grams of nitrogen and 11.2 grams of oxygen. Only nitrogen and oxygen, and we give you the molar mass of 92. Here are your steps. Let's start with the empirical formula, and we see it's quite simple. We divide by the nitrogen and the oxygen atomic mass and get the number of moles. We then divide by the smallest number, 0.350, and we get a ratio of 1 to 2. The empirical formula mass of NO2 is 46.01. We then take the molecular mass and divide by that empirical formula mass, and we get 2. So the molecular formula for this compound is twice the empirical formula, or N2O4. Here's one that you can simply take down and do at your convenience. You can find the empirical and the molecular formula of this using the method that we did before. You may want to review the previous slides so that you can see exactly step by step how it's done.